It is fascinating to see what Ethereum blockchain upgrades bring for its users. After the merge, along with adding network security, scalability, developers are also focused on better use cases for validators and staking pools. If you are one of those interested in learning more about Dencun featured EIPs, stay with us. Welcome to PEEPanEIP episode 117. I'm Pooja Ranjan, back with another special episode on Dencun Upgrade. Documented in February 2022, co-authored by Alex Stokes, Ansgar Dietrich, Danny Ryan, Martin Swente, and Lightline, EIP-4788 Beacon Root in EVM is a proposal to support a wide variety of use cases that improve trust assumptions of staking pool, restaking constructions, smart contract bridges, MEV mitigations, and more. To learn more about the proposal, let's welcome Alex Stokes. Welcome to PEEPanEIP, Alex.
Thanks, Pooja. Happy to be here.
It's great to see you back. For those who aren't aware, Alex is a researcher at Ethereum Foundation, and he is also building MEV Boost community by organizing community calls. He has been generous enough to take out time and talk about Ethereum improvement proposals and other ongoing research work. In the past, he enlightened us with talks on MEV Boost, EIP-4888 beacon chain push withdrawals, EIP-44's bound historical data in execution clients, account reforming with Altair upgrade. So if you have missed any of these, check out PEEPanEIP playlist on eCatherdus YouTube. Moving on, today we are here to learn about EIP-4788. But before we go there, for our new subscribers, may I invite Alex to say a few words about himself and his journey in the Ethereum ecosystem.
Yeah, I think Pooja was saying I'm a researcher at the EF, doing a number of things at this point. And so, yeah, looking into various topics. Historically, I had worked, looking at proof of stake and the different consensus things that we've done leading up to the merge. And then now, there's some things that we could still hope to improve around the staking model. One of them being the stuff we'll look at with the CIP. And yeah, from there, it also kind of opens a whole box of different things we've introduced to Ethereum in the form of like MEV, restaking, and all this fun stuff. So I've also been looking into some of that lately.
Thank you so much. I hope it inspires someone to join the ecosystem. Without further ado, let's peep in.
Let's go ahead and dive in. So yeah, if you're watching this, you have probably heard of this. Ethereum has merged. Anniversary is coming up soon. And yeah, we moved from proof of work to proof of stake. And the way that we chose to do this was essentially with this dual layer architecture. So you can imagine there's like a consensus layer that is like figuring out sort of what has happened in the world of Ethereum. And that consensus layer somehow houses this execution layer. So the idea with the merge is that you had this proof of work chain that was like coming along, and essentially it was the consensus was kind of like hot swapped in place. So that you have the execution layer where all of our applications live, and then now there's a consensus layer that is forming consensus over, again, the protocol. So a lot of that was reflecting sort of just, the historical, let's say progress of both of these different efforts. And in order to merge them, this was probably the simplest, but that left some things to be desired. Some things around the staking protocol that we could think to improve. And one of them is very much just even communication between the layers. This is even reflected if you're like a validator and like the life cycle of like ETH to sort of stake and unstake. So, what you could do sort of immediately at the point of the merge was sort of deposit ETH into the deposit contracts, moving that from the execution layer to the consensus layer. And it actually wasn't until the Shapella hard fork that we had earlier that you could actually withdraw the ETH from the consensus layer to the execution layer. So what I was saying is that you had a way to move ETH from the execution layer to the consensus layer, and this is like some form of communication, even if it's like very limited, just like moving ETH. And actually, yeah, at the point of the merge, there was no way to even go back the other direction and withdraw your ETH from the CL to the EL. These are like these fun little acronyms we like to use because consensus layer is a mouthful, as is execution layer. So that being said, there's other things we could imagine trying to like sort of communicate, especially in like a trustless way from one layer to another, beyond just like, okay, this ETH balance moved from here to there. There's a lot going on because there is all of this like sort of crypto economic security at the consensus layer with all of the ETH that has been staked. There's like a whole life, like a validator life cycle, and there's like various applications that you can imagine. Some of them we'll look at in a bit that tie into like understanding this information. And if there are a way to like somehow gain information about, that state inside the execution state that we all know and love, that would actually improve the trust assumptions of many of these applications. So EIP sets out to do is actually, essentially close the gap from not only going from sort of the CL or the EL to the CL, but then back again. And like I've been gesturing at, there's like all sorts of applications that you could imagine, building with this. And, that being said, many of these, just to run through them. I mean, again, there's probably even more that you can imagine. Some big ones are like staking pools. So these like liquid staking tokens, Lido, Rocket Pool, things like this. They essentially need to know the state of the validators on the consensus layer in order for them to be able to like, even function, right? Like you need to understand, okay, if this validator is in this pool and is supposed to have done this, like did they? And if they didn't, what does that mean? Restaking applications like EigenLayer. So people now are thinking about, okay, if we have all this like stake locked up, well, that might be like capital inefficient. So we could imagine sort of repurposing it in other applications. And again, all the same considerations apply. If a validator is supposed to do this, what do they actually do? And what does that mean for my protocol, my application? Another one is around MEV management. This one I think is like maybe a bit more speculative than the others, but there are some constructions you might have heard of like PEP-C, where again, you could very much imagine wanting to know sort of the behavior of validators or like MEV builders in this case in the system and understanding what they did and using that to actually improve the security of whatever application you're designing. And that all being said, many of these applications exist today. I mean, I gave you some of these like products in the market already. And, so it's not that people have like not, been doing this stuff at all. In fact, a lot of motivation for this EIP is just recognizing, hey, people are going to do this. So like, if we can improve the security of the whole thing, like that would be great. And this is one way to do this because right now, the way all these applications work is they have some sort of trusted oracle. You can imagine just like a multi-sig that is basically authorized to like vote in like the latest consensus state. And that's essentially how all these work today. With this EIP, you could actually remove this oracle entirely and instead have this trustless one. So that's very much the motivation for this work here. And yeah, so EIP-4788, this is again the EIP that is, trying to execute everything I just said. So we will, in some way, get the beacon block root from this beacon chain, essentially the consensus part of the protocol that the EVM cannot currently access. We'll somehow move this root into the EVM. And I'll explain a bit more what sort of like this root thing is and some of these other words in a second. But yeah, you can see here that the EIP's been open in some form for like over a year now. And yeah, at this point has quite a long author list. So yeah, let's look at the EIP a bit closer. So a big thing here is this concept of a beacon block root. And with the merge, maybe this makes like a little less sense because there's just like the merge chain now. But before the merge, there was a proof of stake chain called the beacon chain. And so when we refer to like accessing the consensus state, we very much want to have access to this beacon state or this, this consensus state. And it turns out that there's like a number of these things, we call them roots. What they refer to are roots of Merkle trees, which again, I'll explain more in just a second, but ultimately they're cryptographic commitments to the data they commit to. And that means you can make efficient proofs against them. And that's very handy. And, as you can probably already see, that's how we start to get to this place where we can make these like trustless statements about the consensus state and then verify them inside the EVM. So we have these accumulators, these roots, and where they come from is that the way we kind of lay out our data in the consensus layer is with this schema called SSZ, and it supports Merkleization just as part of it, where you can say for some given piece of data, I want to also be able to make a Merkle tree. I can take the root of this tree, and that gives me a commitment to all the data. This is very handy because now you can have Merkle proofs to say, yes, if I trust the root of this thing, then in fact, I can actually say, okay, this root committed to this data at this point in time, and we're good to go. So this is a schematic of kind of what I was just gesturing at. So at the very top left here, you see, I said 0x beef cafe. That's like some hex encoding of this root. These roots are like 32-byte values. And again, are these cryptographic commitments to all this data. So for example, you can imagine having the root here of a beacon block. And the way this works is that ultimately the root here commits to the header of this block. In turn, the header commits to the body. That's where you see this body root. But it also commits to other things like the state root. So then you can see from the state root, we could have a proof down to the beacon state. The beacon state has all kinds of things. For example, the registry of validators. You can imagine making a proof to like one validator in this list. And then from that one validator, you say, okay, for example, I could prove against this very top level root. So at that point in time, as of the state of the chain, was this validator slashed? And here, I'd like to paint this picture that, yeah, basically you could reach any consensus state from this root. And we have these fairly small proofs to do this. And yeah, we now unlock all this information we can use to like harden these different applications and protocols I was talking about a second ago. So that's pretty cool. Now, that's sort of just like, to give you context when we talk about getting the root in the EVM, like what do we mean and how does that help us solve our problem, which is like making proofs about the consensus state. So we now have a way to like make proofs about them. The thing is we now have to get them like in the EVM. So that's kind of like the other half of this EIP. And to explain that, we will need a little more additional context as well. So with the way that the software is structured today, we have this thing called the engine API. It's like a very core part of the merge. You can imagine other like CL and EL software that doesn't use the engine API. They could have like more of a tight end process integration. There's also things you can imagine, but essentially this engine API gives you like a sort of minimum functionality. It says, if you are like part of this ecosystem, then there's a way for like, for example, the EL to get updates about the latest head of the chain. For example, for the CL to like understand if this EL block is valid, things like this. And I have this little graphic here. So essentially there's like different APIs. Generally we see clients built like this with like different separate clients talking over the APIs. And, they each separately have their own like gossip network, peer-to-peer network at each layer of the stack. So the reason I brought this up is because we essentially will use this engine API here to communicate this root. And at a very high level, what does this look like? Well, essentially for every block, the CL will send this parent beacon block root. And, just to make this clear, the reason we use the parent is because you need this thing available to actually execute the block, which means you need it to construct the block, which means if you use the current block root, you wouldn't be able to get it to have it in the EVM. There's a circular dependency here because you can imagine a very simple smart contract that changes execution just depending on the value of this root. And so, yeah, you can't get the current block root inside the current execution, but that's fine because we'll just use the parent. So the CL goes to send the parent along with an execution payload, which is like some new execution message that it wants the EL to verify. The EL puts it into the execution payload header. So this is here to support like syncing use cases. I think I'll say more in a minute about that. And right, so the EL then takes this root value from the CL, it writes it to the EVM state as a system transaction. So this is a new concept this EIP introduces. I'll say a bit more in a second, but essentially there's almost this new class of operation or transaction that has, I won't say special privileges, but maybe we should say that. It has a way to basically write this in a way that no one else can write. And that helps us, know that the whole construction is secure. So once the EL writes the root that it receives into the EVM state in this like special way, then it's just now in a smart contract, and like anyone can read it like any other smart contract and get the root value that they're looking for. So yeah, I talked about some of this as I was going through the steps. Why do we want to use the parent beacon block root? So again, there's just this circular dependency. You could have like dependent execution based on the root value. So you can't actually like have the root value that's going to commit to the execution if you need the root to be part of the execution. Hopefully that makes sense. And then also we would like to put the block header, or sorry, put the block root into the block header. And this is to support syncing. So there's like a sort of, we'll say design decision of this merge architecture, which is essentially saying that you actually want the EL and the CL to be able to operate independently as much as possible. And so, for example, there could be like a reorg on the CL, and then suddenly there's like some new EL block over here that, you know, the local EL has never seen. It has to say, hey, execution client, like, go tell me if this chain makes sense, because I think I should switch over here. The EL then needs to go sync this this new branch of the chain, and it will go do that. And yeah, you wouldn't want it to be the case where the execution layer is now syncing a branch, and for every block, it has to kind of like go back to the CL and say, hey, what was the root? Hey, what was the root? Hey, what was the root? Instead, they're just all sort of, you know, very neatly committed to in the header, and the EL can kind of just go independently. So yeah, let me talk a bit about the system contract idea. So this is actually pretty new. This is something that has been changed in maybe even the last month. And originally this EIP was written as a precompile. So, you know, we have like an identity precompile, SHA-256, there's various ones. And the idea was essentially have the functionality of this thing be a precompile, and then now it would just be stateful. So that would still be like a twist on the feature set, because all precompiles that we have otherwise are stateless in the sense that, you know, if you just like put in data, you'll get back the same thing no matter what. This would actually be stateful because we'll see in a second, there's actually like somewhat sophisticated contract state that we're keeping track of for reasons I'll explain when we get there. But ultimately, you know, this would be a precompile, it would have state. And we went, you know, there's some back and forth around this design decision. You know, if you're going to get into the weeds, you can go check out the all core devs from maybe like the last month or so, where we talked about some of these things. But ultimately, we've settled on essentially the system contract. So rather than this be a precompile, you ultimately now just like do the same thing, but have it be a smart contract. And there's like a number of reasons to do this. One of them is just that the stateful precompile is like kind of a novel notion, and it's just, there's like less sort of new stuff to think about and reason about, both as like a protocol designer, but also as like protocol implementer, especially from a security perspective, to not have this like new concept. Whereas instead, just like a regular, you know, vanilla smart contract is one that, you know, we as a community have like a lot of experience with, and that's something we like kind of understand, right? So that feels better. There's like another important point, which if there were a problem with this EIP, say an implementation of a precompile, that would ultimately be like consensus failure, which is bad. Because you can imagine there's like two clients, let's say, and they have a difference in the precompile, well, they would just end up with like, for example, a different state root, and then there would be a chain split, and that would be a headache. This way, you know, assuming the EVM is correct, there could be a problem with the contract bytecode, and that might mean that like the feature of this like beacon state root, or sorry, beacon block root, you know, fails for some reason, but it wouldn't mean like a chain split for the protocol. So, you know, that's actually a pretty strong argument for this approach, because it just kind of eliminates this whole class of like greater consensus failures, yeah, beyond what we would have otherwise. So that being said, the reason this is like a system contract and not just a, you know, actual vanilla smart contract is that we still need some way to sort of gate who can like write roots to this thing. For security reasons that I'll get to in a second, we need to write to it a bit carefully and in a certain way. And so you would still need some way to say, okay, even if this is like a contract with EVM bytecode, that's great, but you know, we need some way to gate who can write to it. And that's where now the access control is done in the bytecode. We'll see in a second, but it's essentially from this address that presumably no one knows, and only this like system caller idea can do it, because basically you just do it outside of the actual EVM execution and have these sort of like admin privileges. So this is what we mean when we say this like system contract or system caller idea. And then, like I said, you know, from there, once the thing has been written to, anyone can go and read it just in a usual way with the usual contract call, and that's good. So just to dig into the details a little bit further, there's this concept of the system address that I was gesturing at a second ago. And the idea is that when you get a new block, before you execute any of the transactions, you, as system address, call into this the smart contracts that will be deployed, and you write the root from the header into the contract storage. And then now again, like I was just saying, anyone can go and call the thing. The actual interface is that you call it with the timestamp of the slot you're querying. If the contract has it, you'd get back the parent beacon block root for that slot. And now we have solved our problem. We have trustless access to the beacon state via these Merkle proofs and series of roots and things. And now our applications are off to the races. However, just as I've sort of explained, there might be a few more problems. For example, it's actually hard because I guess, yeah, like one way to think about what I just said is that you would, for each block, you would like go and write the one root, and the next block would overwrite the next root, next block would overwrite the next root, and so on and so on. And so what this means is that you basically, if you want to use this thing, you have to make sure that the transaction you write to verify all these proofs and know that your claim is correct would need to essentially be included in like the same block as the state you're trying to make proofs against. That's actually going to be pretty tricky, and there's just no reason to really like demand this of people. So instead, we can just say, okay, well, rather than like one slot sort of window, we can imagine there's maybe a day of like roots that are lying around. And so now the actual implementation is not just the one root, but it's actually structured as this ring buffer. A ring buffer is, there's this graphic here from Wikipedia, and basically it's just saying like you have like a fixed array, and the idea is you just like use some modular arithmetic to like index into the array, and it just loops around. And yeah, you change it, you pick the size of the buffer to have your window. For example, we'll target say a day. And what this means is like rather than needing to get into like the exact same block that you're trying to make a proof against, you like have some time. You have say a day to like say, okay, I want to make a proof about the slot that just happened, and maybe I will like go off and like figure out, okay, I need to reason about some protocol state now, and then I need to make the proof, and maybe this takes me 5 minutes, and then I can actually get my transaction on chain from there. So this should be much better in terms of UX. Now with the ring buffer, there's like another complication, because essentially we can have missed slots, and the way the interface works is that you can basically query for any slot. When we say missed slot, what we mean is that essentially we expected there to be a beacon block. There was a validator who could have made a beacon block, in this case, a whole merge block, a block in the chain, but for some reason did not make it on chain in time. Either the validator wasn't online, there was a failure in block processing and block production, maybe there was a reorg or something. There's all sorts of things that can happen. And in that case, essentially the block does not make it into the chain, and it's like missed in some sense. And this is what we mean by a missed slot. And this is a problem for this EIP, because essentially what would happen in this case is that you would have, especially, once this thing is deployed and say there's a whole day of roots in here, then now you get back to the same index or the same like cell, let's say, of the string buffer. And if you haven't, if you for some reason missed like writing in the new root, what would happen is you would have the old root, if that makes sense, like modulo say a day. And I tried to make a little graphic here. You can imagine we go along and fill each cell with like a root. So now it has like this nice purple color because there's like good data here. But then we missed a slot right there where there's like the red circle. And that's kind of indicating, okay, so sure, there was a root here, but it was actually the root from like, it would have been that slot modulo the size of the ring buffer, right? So it would have been like yesterday's slot at that point in time, not today's slot that we want. And that would be bad if you could say, hey, give me the root for this slot, and it's just like the wrong information. Like you can imagine somehow you like have a restaking protocol and you need to know, okay, if my validator was slashed at this point in time, like their stake is no longer any good in my thing. And so I need to like do the accounting in the execution layer to make up for that. But if I could somehow make false proofs or proofs about, the incorrect state, then suddenly my thing falls apart. So that's not any good. And the way we fixed this was essentially to make a second ring buffer with the timestamps. And so essentially you can think of it as like cache, where it's saying like, hey, for this timestamp, what was the root that I had? And you actually will only return data if the timestamp matches the one you're querying. And then otherwise you just forget exactly what we say. I think you just return nothing. You do like a revert. So now there's no way to get, let's call it stale data out of the contract. And I lifted the pseudocode from the EIP. I'll just call it some nice things, but essentially it's saying, the things I've just covered. So As you go to execute this thing, you check first, who's calling this contract within the EVM. If it's the special system address, then you actually want to run the set routine. If not, you want to call the get routine. And again, the logic or like the rationale is that no one should be able to like fabricate a transaction from the system address. We just pick this like particular address, and assuming, all of our cryptography is secure, there's no way for someone really to like find the private key for this address and then make a transaction as that sender. So if that's the case, then we can use this to actually know, are we in like the system context or not? And if we are, then we will call the set routine here, which is basically saying, okay, give me the timestamp of the block, turn it into these like indices into each of these separate ring buffers where I'm going to put the timestamp along with, here it says call data, but the understanding is that the call data contains these 32 bytes, the parent beacon block root. If you are not the system address, then you would call the get routine, where again, pretty straightforward. If we have anything other than 32 bytes, we're actually just going to revert because we demand that, because we should only be getting roots into this thing, or sorry, only get timestamps into this thing. And we want the timestamps to just be the word size of the VM. That's just what will naturally come. So then given the timestamp that we're interested in the call data, we convert that into like the same index we expect. We get that from the storage. Again, if they don't match, we just revert actually, which also returns out of this code. Then if they do match, we can go ahead and just read the root in the same way and return that to the caller. So pretty lightweight. Yeah, should be pretty straightforward. So that was looking at implementation. And yeah, from here, like what kind of applications can we imagine? I'll like sketch out a few of them. Hopefully if you're watching this, you have more ideas and, can be off to the races in terms of building all sorts of cool stuff. And yeah, like immediately these are like the ones that have been running. So like staking pools, Lido, Rocket Pool, restaking with EigenLayer, MEV management. And so again, these are things like if you've been following Barnabas, like that Psi idea, you can imagine rather than like have like a very fixed sort of PBS protocol like we do today, you could imagine the actual auction bid is like generic, possibly as generic as you want. And yeah, you could imagine wanting like either validators bonded in the system, builders bonded in the system, different things like this, and wanting to make claims about the consensus state to help make secure constructions there. And right, so I mean, the first thing is immediately all these applications, and even ones we haven't thought of yet, can use 4788 to trustlessly get access to the consensus layer. And that's really big because it instantly improves all the security of like all of them, right? They no longer need these like trusted multisigs to do anything. They just, now have this sort of as a protocol facility, and that's really great. So, I'll drill in a bit to some of these different applications with staking pools, right? So like a very like obvious, like maybe almost too obvious one is just literally knowing, if I have a validator in my staking pool that I want to manage, as a system of smart contracts, are they even registered yet? Like, what is their life cycle? Have they deposited? Are they active? Are they slashed? Are they not active? Have they exited? All these different, attributes that a validator can have, and that's going to have implications for my staking protocol. Similarly, validator performance. So this is like a big one, is saying like, hey, I could actually prove. So we actually, we record validator performance essentially in the beacon state, and by doing so, you can figure out, what rewards or penalties they should incur. And again, should be very straightforward to see how that can be really helpful for a staking pool, because you can now prove what happened and then figure out, maybe there's like some accounting you want to do in the execution layer for this pool. And now you can get this information directly. And yeah, there's like more consequences of this fact. One thing would be actually using like a running stream of this to actually rate the performance of a validator. You can imagine that's like some nice little encapsulated metric, maybe to say give like node operators in Lido like a scorecard of sorts or like a report card. You could then imagine like a more complex staking pool where you actually use performance to actually like make tranches of the LST. So that's like a big thing is, for decentralization reasons, we want LSTs to have like very heterogeneous validator composition. But then, the more heterogeneous they are, the harder it is to have a single LST that like represents all of them. And yeah, you could start to imagine tinkering with things here around like actually making different like classes of risk based on validator performance. yeah, there's like a whole fun R&D space there. Yeah, I'll just say that for now. And yeah, restaking, I mean, again, like even very simple basic things like, is the validator registered in a way that they can participate in my restaking protocol? Like the way, at least like Eigenlayer and probably most or like even really all restaking constructions you can imagine, they're going to, the way that they work is basically as a validator, you can have stake at the consensus layer, but then when it comes back to the execution layer, it basically needs to flow through the restaking protocol in the execution layer. And that's actually where the accounting will happen. So if there are any slashings there, they can be accounted for. And otherwise, yeah, these like restaking apps are like meaningless, or rather they don't have any security. So this is like a very critical part. So you can actually check, hey, is this validator correctly registered to even participate in my application in the first place? Another one, yeah, is understanding like our validator is slashed. So this is saying like, well, yeah, with any restaking broadly, there's this mismatch almost because you have the stake at the CL, and that's where like independently things could happen. There could be like consensus faults or consensus penalties, less harshly, that can happen there. And then separately, you have this whole app layer where you could have like app layer slashings or app layer penalties. And like already these things are just like completely out of sync, which is actually like not great for security of either the application or the consensus layer. But that all being said, you can imagine restaking constructions where like there's a much tighter sync between these two values. And then actually what happens is like the whole thing is more secure, simply because like if I'm slashed at the CL, that's probably going to have implications for my application layer validation. If I'm slashed in my application layer app, then that's going to have implications, like I should actually maybe almost be slashed as much as I am in the, or, if I have some penalty from an application failure, that should probably be upstream, so to speak, into my consensus representation as well. Yeah, there's more I could say about that, but restaking definitely will, be improved or would very much need access to this type of information that this EIP provides. This one I kind of said was more speculative, but again, just like MEV management, there's many things we want to do around like improving the trust model of MevBoost, which is our off-chain PBS. And ultimately it just means like iterating different bits of the design towards more of like what an enshrined PBS would look like. And yeah, this is more like a very high level type of thing we can imagine. But yeah, there's this notion of PEP-C, which is saying, okay, if there's like a fixed auction format with MevBoost today, what if this was actually like a programmable thing you could do? And then you could very much imagine wanting to have like access to this consensus layer stake to do different things. And yeah, from there, like, I'd very much like to be surprised. Like there's so much that I think we can imagine that, is sort of enabled or at least hardened by like the CIP. And while it does seem like pretty small in scope, I think given, the value of the information that it sort of enables, there's a lot that could happen, whether that's like better stake pooling constructions, whether that's better restaking constructions, or other things like this. So I think that was all I had for now. And yeah, if there's some questions, I'm happy to take some questions.
Well, thank you so much, Alex, for the presentation. It was really interesting to follow the evolution of the proposal. I sure have a few questions on that. We'll get there in a bit. But other than that, I love the pseudocode in EIP. I'm not sure if I have ever seen pseudocode added in any of the EIP. I've seen people adding, especially on ERC side, some of the Solidity code and code proposals sometimes have Python, but it was nice to see pseudocode there. And I followed the post on PEP-C. We'll be sure to have Barnaby Manath on the show to talk more about it. And about the implementation, I hope to see more implementation of this proposal in near future. People here on the call today, if you have any question, feel free to either raise a hand or maybe put it on the chat so I can invite you. In the meantime, I would like to start with the first question, as you mentioned in your talk about the ACDC or ACDE meeting discussion. I'm wondering about the relationship with EIP-210. So in earlier ACDE meeting, Martin Swande mentioned about the proposal, which was originally proposed for block hash refactoring by Vitalik Buterin. And the proposal isn't stagnant. That means we never implemented that. Things have changed. Now we are in the proof of stake world. So my question to you is, do you see EIP 4788 as an extension of EIP 210 in more related word? Or do you think that we have carried anything from those proposals, or these proposals are independent of each other?
Yeah, I would definitely say that at least like the thinking behind 210 is reflected here. So maybe I have my numbers off, but I believe that the point there was essentially to move the block hashes. So already today we have access in a very similar way. You can get access to these like cryptographic, we don't call them roots, but we have like hashes of the execution block headers. Those are in the EVM. And so if you want to make proofs about the execution state, you can kind of do this in a very similar way. And the way it works today is that there's just this this opcode block hash that gives you access to say the last 256 of these execution hashes. And yeah, from there you can like make proofs, verify proofs however you want in the EVM. And I think, again, if I'm misremembering a different EIP, just let me know. But I believe with 210, the idea was we would essentially refactor this so that we would move them from like this opcode format actually into the EVM state, very much how like 4788 is doing. And this is actually where the relation is there was a design decision with this EIP to actually not copy the block hash opcode approach and do more of this like, data's in the state approach with this EIP. The reason why is because we want to support stateless execution. This is a different call, but there's the whole Merkle effort and moving from a Merkle Patricia trie that we have today to a Merkle trie. And there's many reasons we want to do this. One of them is that it actually will support efficient proofs about the consensus state the execution state. And this is helpful. Well, it's helpful for all sorts of reasons. You can make stateless clients. And stateless clients are cool because it means there's like fewer resources required to like run a full node. And that's really great because it should, again, just lower barriers to entry, which is really good in terms of running a node. And concretely, the thing that 210 and also this EIP, tries to address in that way is like harmonize with this fact that if we have stateless clients, it's better if we have as much or even the entire protocol sort of represented in the state. And, this is kind of a long-winded way to say this, but ultimately the whole point was that with the block hash construction today, it's not just the state you need, but also there's this like other little piece of data that's like almost like a look-aside buffer or something of the block hashes. It's like these block hashes are not committed to in the state and they're just kind of out there. And so if you actually want to like, for example, make like a stateless proof of like some block, you would, in the current regime, need to actually include this other piece of data as well, which is like, it's not the end of the world, but it does mean like bigger proofs and also just like one more thing to think about. And then that actually has like, I think, pretty profound implications to implementation. Are there bugs in the client? Like, is the client secure and all of this? So it's far simpler just to say, hey, if we have this like unified approach to like accessing state, that's like much preferred. And that's definitely what that EIP was trying to do, and also what this one is doing by putting the data, like the history almost we care about, directly in the state.
That sounds good. Perhaps this is the time that we can move the proposal 210 to withdrawn when we have 4788 deployed on the mainnet. All right, moving to maybe a similar question. I'm talking about EIP 4788 version 2. Originally written as a pre-compile, EIP 4788 is on the table for quite some time, but we saw some different discussion points on various core dev calls. We saw the PR 7456 by Matt, and again, this is called as version 2 for this proposal. I'm curious, what changed in EIP 4788 from version 1 to version 2 and why we brought that change?
Yeah, so the main thing was moving from a precompile approach to implement the EIP to this system contract idea that I was discussing. So, right, like rather than have a native implementation that you would call out where like there would be some state, but it would just be attached to like almost this like native EVM bytecode. That doesn't really make sense, but almost like native bytecode, you can think of it as. And instead now we have it very much looks like a regular contract with EVM bytecode that's interpreted. And yeah, there's contract storage just like any other contract could have. And the reason we went with this, I tried to call this out with this notion that there's like a big security argument, which is that basically if there were a problem with the precompile, say between implementation of two clients, that actually leads to like a consistent split, because like one execution client would think this and someone else would think this, and now there's a chain split. These are bad and should be avoided at like most cost. And one way to do that is you can actually say, okay, rather than sort of pull in like an even bigger base of implementation that needs to be correct and vetted and all of this to know that this is not going to happen, we can actually like restrict the scope by moving to like a fully sort of hosted implementation, let's say, inside the EVM. And that's ultimately what this EIP is doing now with V2. And yeah, the thing is there could still be a bug in the implementation, but what it would mean is that, okay, maybe now the security of this Oracle is broken, like you're getting back a stale or like just an incorrect block route, which would also be bad, especially for all these applications I was talking about. But you would avoid this chain split because basically the client would still compute a chain and the chains would all be in lockstep, even if like the application doesn't make any sense. So, I think all in, we all thought that was like a very compelling reason to switch to this new version, and that should be what's shipping in Deneb, Cancun.
That's awesome. Security is always a very compelling reason. Talking about security consideration, I find that section as to do as of now in the EIP. I would highly appreciate, adding something over there, like what are the security consideration that client should be aware of while implementing, or anything that makes more relevance to implementers of this proposal. All right. My next question is about changes on CL clients. So this EIP involves both layers. The proposal reads as exposing beacon root inside the EVM allows for trust minimized access to the consensus layer. Yet this EIP is listed as execution layer EIP. Does it mean spec changes are only for EL, and on CL client it is either minimal or none, or is it because it is getting into system contract?
Right. So there are some changes at the consensus layer to support this. They're actually quite minimal, like even smaller than on the EL side. And essentially it's just saying that when I go to produce a block, the CL will also need to send over the root, which is what the EL will put into its execution payload. And then, the rest kind of follows from there. So there's essentially a small change to the engine API during block production, but that's pretty much it. So yeah, pretty lightweight. And yeah, I think from the CL side, this EIP has been ready to go for quite some time. And then now we're just kind of fine tuning more of the EL stuff.
That's right. My next question is about the timing. The proposal was drafted in February 2022, and we have had at least 2 upgrades since then. Both of them were major upgrades. Why it couldn't have been considered earlier? I'm more looking into the roadblockers, if there were any, and not the upgrade priorities.
Right. Maybe could you ask again? It's just the question is like, why did we were there any blockers to shipping this sooner?
Right. Yeah. I understand the 2 upgrades which happened in between February till date are March and Chapela. They both had their own priorities. If priority was not the reason, I'm just trying to understand the status of EIP and why we could not have shipped it in earlier upgrade.
Right. Yeah. Fair question. I mean, I think it is mostly just priority though. We wouldn't we did pretty much everything we could to ship, just the merge and not anything else. And then from there, the question was like, okay, well, there's actually this other really big piece, which is withdrawals. So then we wanted to ship that. And then, yeah, I mean, conceivably we could have included this in an earlier fork, but yeah, there wasn't enough sort of bandwidth amongst the core devs, or yeah, I guess just not enough pressure from, say, the community. So it wasn't it didn't make the cut. We can only put so many things into each hard fork, but I am excited this one's going into the next one, and yeah, it unlocks other stuff we want to do in the future as well.
Thank you. I see there is a question in the chat by Andrew. Andrew, please go ahead with your question.
Sure, thanks, Pooja, and hey, Alex. My question is just kind of clarifying around the implications for liquid staking protocols and like the removal of trust assumptions around the oracles for these protocols. I think really my question's more of like a technically how it works from deriving like something like the validator effective balance from the consensus layer block root that's now exposed in the EVM. I'm just wondering if that's still something that requires a trusted actor to perform, or if there's a way that it can be done trustlessly by an immutable smart contract or something.
Right. That's a really good question. So that's certainly like, again, like I think a very big motivation of this work is just to say, yeah, like how much can we imagine these different applications like staking pools, and like, can we make them, totally trustless? And for example, if they need to like prove off the effective balance of some validator, that's great. But then, yeah, it's like, maybe they have trustless access to the data, but yeah. So either way, it's a good question, because actually the answer is there's still some pieces that we may want to consider another EIP where you would actually even like fully remove any trusted bits. And the trusted bits I'm getting at is that there are some things in the beacon state where we actually may want to change the layout of different data, and that actually changes the format of the proof itself. So you could imagine that basically, yeah, we don't really have time to get into it, but ultimately there's this notion of like a generalized index, which says if I have some data, there's a way to go from the roots to like exactly the data I want. And, as protocol designers, we tried to not basically make these indices change, but like they can. In that case, yeah, you would imagine that you kind of need some governance process to update your application with like this new information. So, in the long run, maybe, these indices I'm talking about will never change, so it's never an issue. Maybe there's another EIP that's like essentially just like a more abstract proof verification precompile. And, you could essentially subsume this functionality and make the whole thing fully trustless. Yeah. So there's like certainly some further research we could do there to probably improve this even further. But that being said, the only time these things then, this data I'm talking about would change would be at like across hard forks. So it's not something that is like even a super urgent risk, even after deploying this EIP.
Thank you so much, Alex. I know it is about time. I just wanted to let you know, I see the proposal is still in the draft status. I would highly recommend it to be moved towards the review status. But before you make the pull request, it would be really nice to see test cases, reference implementation, and security consideration section, which is still mentioned as to do, have some words over there. I know the proposal is already on DevNet, so it would be nice to fill up and move the proposal as desired.
Sure. Yeah, I will. I'll keep the status in mind.
And any final words if you would like to share with the community?
Yeah, otherwise, no. I mean, thank you all for having me. Hopefully this was helpful and like at least shared some of the thinking and the context that went into this. Yeah, otherwise, definitely consider this. If you need this information in your application, like please take a look. Feel free to reach out if you want, and we can chat about how to integrate it into your application. And yeah, otherwise, I think that's it for now.
Very well. Alex Stokes, we thank you for joining us on PEEPanEIP and talking about upcoming changes with EIP-4788. We look forward to seeing this proposal on the public testnet and finally on the mainnet with Dencon. On this note, thank you to all our YouTube viewers for watching and podcast subscriber for listening to this special episode. Should you have any question on this or any other topic, let us know at ETHCatHerders Discord. Check out the description for more info. We'll be back with another interesting talk. Until next time, keep watching, keep listening, and keep sharing your love with Ethereum cat herders. Cheers.